Hey everyone, and welcome. You've seen them 1,000 times, right? Those giant modern wind turbines. But I'm gonna bet they have some incredible hidden talents you've never heard of, and they go way beyond just catching a breeze. So let's dive in.
So you're driving down the highway, you see them dotting the landscape, these huge structures spinning away. But are they all basically the same machine? Oh, absolutely not. The evolution of wind turbine tech is this really fascinating story of turning a pretty simple windmill into a super sophisticated grid stabilizing powerhouse. Okay, so here's the fundamental problem that engineers had to crack. Wind is, well, it's chaotic. It gusts, it dies down, it changes direction on a dime. But our electrical grid, it's the complete opposite. It demands a perfectly stable, consistent, and predictable supply of power. The entire history of wind turbine design is really about building a bridge between that unruly force of nature and our very, very orderly power system. At its very core, every single wind turbine does two basic things. First, its blades grab the kinetic energy from the wind and turn it into the mechanical energy of a spinning shaft. That's step one. Then, for step two, that spinning shaft gets hooked up to a generator, which turns that mechanical motion into electricity. Sounds simple enough, doesn't it? But the real genius is in how modern turbines control those two steps. This right here shows the two big ways of doing that. The old school method was called stall regulation. The blades were shaped so that if the winds got dangerously high, the airflow would get all turbulent, causing the blade to stall and naturally shed some of that power. It's simple, it's tough, but the modern way is pitch regulation, where little motors in the hub are actively twisting or pitching the blades to the perfect angle second by second. This maximizes energy when winds are light and protects the turbine when they're howling. It's really the difference between a sledgehammer and a scalpel. So let's start with that first generation. We're talking about the fixed-speed turbines. These were the workhorses that proved wind power could actually work. You can think of them as the reliable old pickup trucks of the wind world. They got the job done, but not a lot of finesse. The first big design is what we call the Type 1. It uses a really simple and tough kind of motor, a squirrel cage induction generator, and it's wired directly to the grid. Now, that direct connection means its spinning speed is locked to the grid's frequency. It's kind of like a car that's stuck in first gear. It works, sure, but only in a very narrow range of wind speeds. Any sudden gust of wind creates a big jolt of power on the grid. Not ideal. So, the Type 2 was a pretty clever little upgrade. It uses a more complicated generator that has basically a big dimmer switch, a variable resistor. This let it vary its speed just a little bit, maybe 10% or so, which was just enough to help smooth out some of those wind gusts. To go back to our car analogy, this is like adding a second gear. You get a little more flexibility, but it's still a fundamentally rigid system. And this is where the revolution happens. The entire game changed with the arrival of sophisticated power electronics. This technology acts like a buffer, like a perfect translator between the chaotic wind on one side and the stable grid on the other, and it completely unleashed the turbine's true potential. Here's how. The first truly revolutionary design is the Type 3, better known as the doubly fed induction generator, or DFIG for short. Instead of a simple resistor, this thing has a sophisticated power converter that injects a perfectly controlled AC current right into the generator's rotor. This completely decouples the mechanical speed of the blades from the electrical frequency of the grid. It lets the turbine speed up or slow down to perfectly match the wind. Now, the engineering brilliance of the DFIG is right here on this slide. The power converters only have to handle about 30% of the turbine's total power. Think about that. By injecting a relatively small controlled amount of power into the rotor, they can control 100% of the power flowing out to the grid. It's this incredibly efficient lever that lets the turbine operate in a huge speed range, both faster and slower than the grid's natural frequency, all while using smaller, cheaper electronics. Just brilliant. The next step in this evolution is the Type 4, or the full converter turbine. This design takes that decoupling idea and just runs with it. Here, all of the power from the generator flows through a full-sized converter. This gives the turbine total freedom. The generator can spin at whatever speed is most efficient for the wind at that exact moment, producing what's called wild AC, which the converter then perfectly cleans up and transforms into grid-ready power. And finally, we get to the Type 5, which is a really cool hybrid design. It uses a variable speed front end, just like the others, but then it feeds that power into this highly advanced gearbox, a torque and speed converter that spits out a perfectly constant speed on the other side.
This allows it to connect to a synchronous generator, the exact same kind you'd find in a traditional coal or gas power plant. It's the best of both worlds, a variable speed turbine that looks and acts just like a conventional power station to the grid.
Okay, so we've got all these different types, but why does it matter? Who cares? Well, this is where we get to the real payoff. These advanced designs don't just produce power anymore, they have superpowers that let them actively support and stabilize the entire electrical grid. So why does all this matter? Well, a big piece of it comes down to grid voltage, which has to be kept incredibly stable. The old Type 1 and 2 turbines couldn't help with this at all. In fact, they actually consumed something called reactive power. You can think of it as the magnetic muscle needed to move electricity, which could actually drag the voltage down. But modern turbines, thanks to their fancy electronics, can act like a voltage regulator, either generating or absorbing this reactive power whenever the grid needs it.
And the difference in what they can do is just staggering. The ability of older turbines to support the grid was minimal, almost an afterthought. But just look at the modern turbines. Their capability is massive. And what's more important, it's controllable. This isn't just some little feature. It's a vital service that helps keep the lights on for everyone. It is a genuine superpower.
But where does this superpower matter the most? Well, it matters during a crisis. When something goes wrong on the grid, say a transmission line gets hit by lightning, how the power generators respond in those first few milliseconds is absolutely critical.
And this right here is probably the single biggest difference. In the old days, when a fault made the grid voltage suddenly collapse, the old Type 1 and 2 turbines were programmed to just disconnect immediately to save themselves. They were a liability when you needed them most. But modern turbines? They're totally different. They're programmed with something called fault ride-through. They see the voltage sag, and instead of running away, they stay connected and actively inject power to help the grid recover.
And get this, a Type 5 turbine with that synchronous generator can pump out over 4 times its rated current during a fault. This is exactly the kind of emergency response a grid operator expects from a big conventional gas or coal plant. Modern wind turbines don't just make energy anymore, they are active guardians of grid stability. And that really brings us to the key takeaway, which this quote sums up perfectly. The behavior of a modern turbine isn't just about physics and mechanics anymore. Its response, its capabilities, its superpowers, they are all dictated by software and control systems. These aren't just windmills anymore. They are sophisticated, programmable grid assets. So that leaves us with a pretty fascinating final thought. We've watched these turbines evolve from rigid, simple machines into smart, responsive grid supporters. But as we move toward a future where they aren't just supplementing the grid, but are the backbone of the grid, what new superpowers will we need to program into them next? What new challenges will they have to solve? You can be sure this evolution is far from over.